It's a pleasure to be here. I would like to thank the organizers, the Crafoord Foundation, and the Academy. And I'm splitting the different global modes of solar oscillations into two categories. The modes here, which would exist even if we were to switch off rotation. And then the modes here on the right, the modes that owe their existence to rotation. Okay? For the first one, of course, they include the pressure modes, the P modes, which have been so useful in learning about the solar interior, especially the sound speed and the differential rotation profile. Okay. All right. And we owe a lot to these two gentlemen for developing the methods that enabled us to interpret the frequencies of the P modes. So my talk is about the inertial modes, which were already introduced by Connie. And the inertial modes are modes that have frequencies of order the rotation frequency, which means, in this case, frequencies that are more than 1,000 times smaller than the frequencies of the P modes. So we're talking about a range below 1 microhertz. I remind you that the rotation period of the sun is about 25, 26 days at the equator. Now, these modes are, the ones that we see in the sun are retrograde in the Carrington frame, meaning that they propagate against rotation if we place ourselves in a frame that co-rotates with the sun at the equatorial rate, or close to it. These modes are seen only in the horizontal component of motion, v theta, v phi. Theta is for co-latitude, phi is for longitude. And their eigenfunctions are best described by their radial vorticity. So they are very promising to probe the solar interior in a different way than has been done so far with the P modes. And I will try to show a few examples of this during this talk. Now there's also, and I should add that, and we've heard it just before my talk here, that the inertial modes have been seen also in stars. Yeah. Maybe they're not exactly the ones that I'm talking about here, but some of them are very likely in common. On the right, I have an additional column here, which is for the global modes of rotating convection. So these modes are predicted in simulations. These are called either booster columns or thermal Rossby modes. They are also the Coriolis force also plays an important role, and they propagate prograde in the rotating frame. Now, they haven't been seen on the sun, but they are believed to play an important role in the interior. Perhaps they drive differential rotation. How do we see the inertial modes of the sun? So we use actually P-mode helioseismology to find the inertial modes. Because the frequencies are so far apart, we can use the P-modes to make maps of the horizontal flows near the solar surface at a cadence of about 1 day, say. And so we obtain movies like this. This is a movie of the longitudinal component of velocity near the solar surface, using SDO-HMI data as input. And we have years of such data. So to find the inertial modes, we apply a Fourier transform in longitude and time to decompose the data into components proportional to exponential Im phi minus I omega t. M is the azimuthal order, or the longitudinal wave number. Phi, the longitude. Omega, the cyclic frequency. And then what we do is compute the power spectrum at fixed m as a function of the frequency and as a function of the latitude, which are the two variables that remain. And so let's look maybe at this column here. So in order to find a global mode of oscillation, what we want is to be able to identify a frequency in the sun which is the exact same wherever we look. So for whatever latitude we're talking about. That's the definition of a mode. Yeah? So a mode would appear in a plot like this as a vertical bar. Yeah? In this particular case, when we plot the power, we see mostly excess power above 60 degrees at a frequency close to minus 86 nanohertz. But if we actually make slices at different latitudes, low latitudes, we see that this frequency shows up as at all these latitudes. So we are really in the presence here of a global mode of oscillation. Okay? And we call this particular mode a high latitude mode just because it has large amplitudes at high latitudes. Now we can, in the case of the sun, we have images. So what we can do is filter the data in a window around that frequency and transform back. And so we obtain the eigenfunctions directly. Okay? And you see here that the eigenfunction in the phi component of the velocity here looks like a spiral pattern. And the whole thing rotates retrograde in the Carrington frame as a block. Yeah? Now the amplitude here is about plus minus, at least on this scale, 11 meters per second. So it's actually a fairly significant amplitude. It is small, definitely compared to the rotation, which is 2 kilometers per second. But it is not that small compared to other components of motion, like the torsional oscillation, for example, or the meridional flow. Okay. And here you have, so you have 4 different modes that have been selected because they actually look different. So this one, we call it either a mid-latitude mode or a critical latitude mode. And this one, an equatorial Rossby mode. Okay. Now, you saw in the previous movie that the eigenfunctions are actually not spherical harmonics. That's important. Except in the case of this mode, where the eigenfunction in u theta looks quite close to a spherical harmonic function. Okay. And actually, we are able to identify the equatorial Rossby modes because their dispersion relation is very close to that of the sectoral Rossby modes that are known to exist in a uniformly rotating star. Okay, so here there's no doubt that we're looking at sectoral Rossby modes or something very close to it. The assumption of uniform rotation, however, is much too simplified to explain and identify the other modes. So the next step that we've done in the analysis is to take into account latitudinal differential rotation. The sun rotates more slowly at higher latitudes than at the equator. And in this particular study, we started with a 2D problem, looking for purely toroidal modes on a differentially rotating spherical surface. And what we find is a very important feature, which are critical latitudes. Each mode, or almost all of them, has a critical latitude where its phase speed equals the rotational velocity at that latitude. And these critical latitudes really have a big effect on the eigenfunctions. Okay, as you can see for this linear eigenvalue problem here, the eigenfunctions look very different for very different from spherical harmonics. These horizontal lines here indicate the position of the critical latitude. Okay. So here we have, so this is what we would call a high latitude mode. This is a highly damped mode, very fast oscillations around the critical latitude. This mode would not be able to be singled out in the power spectrum. The lifetimes are way too short. This is a critical latitude mode or Santem mode. And the equatorial Rossby mode, which is not too far from spherical harmonics. So now we go to the next step. And this is work done mostly by Yuto Beki at our institute. He tried to take into account all the physics and to solve the eigenvalue problem in 3D, or more precisely in 2.5D, because we assume the EIM phi dependence of the mode. So very important is to take the realistic differential rotation profile inferred from P-mode helioseismology. Okay, this is what you see here. This is the angular velocity in nanohertz throughout the convection zone, faster equator than poles. There is realistic background stratification in the model. And one thing that Yuto was able to find out is that it's very important to also include a latitudinal entropy gradient in the model. The sun has to have a latitudinal entropy gradient that is required to explain this differential rotation profile, which is not constant on cylinders. And in terms of temperature, this means that there is a maximum temperature difference between the pole and the equator of about, well, between 7 and 10 degrees, with the poles being hotter. So this has to be included in the background model in order to compute the proper eigenfrequencies and eigenfunctions. And in addition, the answer depends on the value of the turbulent viscosity in the model and the superideopaticity, which are two quantities that are very, not very well known, but are very interesting for other problems. So here you have, on the left, the observations for the three selected modes that I showed already earlier. And here you have the eigenfunctions from the best models. You see that at the surface, the eigenfunctions look quite close to the observed ones. The frequencies are also quite close. And the advantage of the model here is that we can see inside the convection zone the amplitudes of the velocities associated with the mode. And we see that the velocities do not drop fast with depth as you have for P-modes. Yeah. The amplitude can actually, in some cases, even go up with depth. So that implies, in particular, that the kinetic energy density most of the time peaks deep in the convection zone. So that gives hope to have access to the deep convection zone with this mode. Now, if we compare the frequencies in the best models with the observed frequencies, we can see that we understand quite a few of these branches here in the dispersion relation diagram. So these are the high latitude modes in red. In black, the equatorial Rossby mode. The next question has to do with the amplitudes of the modes. so except for the high latitude mode with m equals 1, most of the modes have amplitudes below 1 to 2 meters per second. And for most of these modes, the explanation is likely that turbulent convection is exciting them in a similar way as P modes are excited by turbulent convection near the surface. Now, how do we explain this large amplitude for this m equals 1 high latitude mode, which is above 10 meters per second, sometimes even above 15 meters per second, depending on when exactly we look in the data? Well, when the entropy gradient is taken into account in the background model, what we see is that the linear eigenmodes are unstable, linearly unstable, yeah? Meaning that there is a positive growth rate. And so these modes are self-excited due to baroclinic instability. So due to this latitudinal entropy gradient. And to understand this amplitude, it means we need to move to something more complicated. Some nonlinear mean-field simulations to understand the mode saturation mechanism. So that's another complicated diagram, which I hope I can simplify in what I tell you. So basically, if we excite in the model a mode due to a particular latitudinal entropy gradient, if this mode has a sufficiently high amplitude, it is going to back react on the rotation, because this mode transports heat towards the equator, transports entropy towards the equator. Okay, so that is the saturation mechanism we were looking for. And then, so the latitudinal differential rotation adapts to the steady state entropy gradient. And in order to be able to reproduce the observed mode amplitudes, we find that a temperature difference between pole and equator of 7 degrees is what is needed. Oh, that gets even more interesting here. I won't go into explaining what this means exactly on the x-axis, but the idea is if we excite this m equals 1 high latitude mode to very high amplitudes, it will back react on the differential rotation in such a way that so differential rotation cannot, latitudinal differential rotation cannot be above a certain value. That's what we see with this curve that reaches a maximum here. Okay, and so we claim here that the m equals 1 mode controls the latitudinal differential rotation. It does not. It probably does not. Yeah, it controls the maximum allowed value for the latitudinal differential rotation. Okay, and when we do simulations in 2D where the modes are not allowed, there is no such saturation mechanism taking place. So the inertial modes in the sun are not only probes of the interior, they also play an important dynamical role. Now here's a question that has been around for a long time. Why can't we see on the sun the prograde modes of rotating convection that exist in the simulations? Okay, for a while it has been seen in simulations that there are convective modes that propagate prograde booster columns of this sort with very large amplitudes, let's say around 50 meters per second. And these are not seen on the sun, at the surface of the sun. Okay. So perhaps one possible option is that these modes are hidden at the surface by the small-scale near-surface convection. Why not? The second option is that perhaps the large-scale convective driving is overestimated in the simulation. such that the solar convection zone is less superadiabatic than expected. And in such a case, we have another question that pops up. How is it that the differential rotation, how is the differential rotation driven and maintained? Okay. So these are difficult questions, given that we do not see this mode at the surface. So I am trying to summarize a little bit here what we've learned. But first, I would like to repeat that we still do not understand the sun's large-scale rotating convection and how it produces differential rotation and meridional circulation as inferred from P-mode helioseismology. These global inertial modes of the sun, I believe, have a great potential since they are sensitive to additional properties of the deep convection zone, such as the entropy gradients, the superadiabaticity, and the modes play a role in the global dynamics of the sun. So I would say here that helioseismology of both P modes and inertial modes still has a very bright future. There's still a lot to learn, and we have fantastic data to do a lot more work. And what I expect also is that some advances in P-mode helioseismology, or let's say local helioseismology, will be used at some point to be able to measure the inertial mode eigenfunctions with depth. Not very deep, perhaps, but there is some hope that we can see below the surface these inertial modes. Now, understanding inertial modes in the sun should help understand these modes in stars. We've already learned a few things, like the eigenfunctions are not spherical harmonics. There's no L in this case, yeah? Well, except for this equatorial Rossby mode. And that, yeah, they also perhaps play an important dynamical role. So we have to keep thinking and observing. And I would like to thank my team at MPS. Here I'm only showing the young ones. Okay? I will say their names here. Damien Fournier, Prithvitosh De, Nelanchal Yoshi, Yash Mandovara, Lakshmi B, Jixiao Liang, Dan Yang, Yuto Beki. Björn Leptin on the left is the student who first saw the equatorial Rossby modes in the data. We also hope to be able to learn something from improved numerical simulations of convection in the sun. There is work that's taking place under this whole sun synergy grant. And very, very important, we really need to keep going with observations of the sun. The Gong network and the HMI instrument are doing a fantastic job at the moment. And I hope that this time series will keep going for a very, very long time, because we know already by now that, for example, these solar inertial modes have amplitudes that are modulated by the solar cycle. So we need to observe for a very long time if we want to understand this. Thank you very much. And I will finish with just a movie. Whoops, no, it's gone. I have a red button here, yeah. Oh, no. One more. Yeah, so it's side to side the observations for this high latitude mode at the surface and the model. And yeah, the model has some advantage sometimes. We can actually not check this, right? And that's why with P-mode helioseismology, maybe there's some hope of being able to confirm this at some point. Thank you.